All right, hey everyone, welcome back to our series on linear algebra lectures. So this is our last video in the series. We'll be talking about change of basis matrices. So the idea behind this is that if you're handed some problem out in the world, sometimes it's easier to solve it in one coordinate system rather than another one. And surely you have by now the experience of having to perform a change of coordinate or change of variables to translate your problem into something that's significantly easier. At the very least, one thing that you've seen this is translation of some curve in the plane. If you had whatever translation of a function, the curve of a function from one to another. It's very easy to work with parent functions, not so much so to work with easier one, some gnarly arbitrary function. And so instead, what we might do is do some transformation of the plane so that the function that you're working with is a unit vector with respect to, is a parent function with respect to your new coordinate system. Okay, so I just have like a little toy problem. We're not actually going to solve, but like just to give you an example, find the area of the parallelogram whose vertices are 0, 0, 1, 2, 3, 4, and 2, 2. Now, however, I don't know how you would want to go about this. If you're very, very clever, you might try and, divide it in half this way. Divide your parallelogram into two triangles. Notice that with respect to the standard basis or standard coordinate system, this triangle, you can compute, you can do like base times height divided by 2 or something like that. And if you work it out, your base ends up being precisely 1. Your height ends up being precisely 2, and it becomes, and so you do base times height divided by 2 is 1. And then you notice that the horizontal line that we drew in order to set up this problem perfectly matched up with half of this parallelogram. And so with some convenient geometry techniques, you can deduce that the area is equal to 2. However, if you view instead of using the coordinate axes, use as basis vectors the vectors 1, 2, and 2, 2, which I've got in blue and red here, respectively. The area of the parallelogram is just the determinant of the vectors two of which, make up two adjacent sides of your parallelogram. Whatever that determinant is going to be the area of that parallelogram. And so in this case, that would be 2, 2, 1, 2, something like that, determinant, which you can do in your head as 4 minus 2 equals 2. So by changing the perspective of whatever basis that we're working with, this problem came down, was taken from the complexity of just like, an old school geometry problem where you have to like slice your shape into a bunch of easier shapes and then find the areas and then reassemble. We're able to take it away from that context and put it into the context of just compute a determinant of a 2x2 matrix, which is mental math, right? In fact, it's kind of just arithmetic. And so that reduction in complexity shows up as a theme throughout nature. Very often, just any time that you're working with matrices and vector spaces, the choice of the basis that you use has the ability to impact the complexity of your problem to extreme levels of swing from one extreme to the other to get extremely easy or extremely difficult. So so we're going to look at just one other example. The question is, so just start with some vector x, which is 5, 1. Right? We'll have two bases for these are all vectors in R2. I didn't say that, but you can tell from the context. we're going to have two bases, b and c. B is going to be -1, 2, and 2, -1. And c will take b 1, 0, and 1, 1. Then the coordinate vector of x with respect to b is 1, 3. You can check that if you just do 1 times the first vector and 3 times the second vector, you'll get 5, 1. And then with respect to c, the vector x is 6 and -1. And again, you can verify that, right? The coordinate vector of x with respect to c. And so we have a problem that we want to solve, which is given y, which is given some vector y. Suppose you know its coordinate vector with respect to b, and suppose you know that it's -1, -2, and then they're asking you to compute the coordinate vector of y with respect to c. Okay, so there are two ways that we can do this. Number one is reminiscent of the problem that we just saw. You can use the coordinate vector of x with respect to b to figure out what the entries in y are. So let's do that real quick. So since the coordinate vector of y with respect to b is -1, -2, we know that -1 times -1, 2 minus 2 times 2, -1, this is equal to y. And if we actually go and compute that linear combination, we end up with, what is that? 1 minus 4 is -3, and -2 plus 2 is 0. Oh, that's nice. Then we have to go and, it's a terrible example. We have to go and compute, we want to compute the coordinate vector of y with respect to c. So what that involves is row reduce the following matrix. 1, 0, the columns of c, right? 1, 0, 1, 1, augmented with -3, 0. Okay, and when you do this row reduction, it's a very easy row reduction. In fact, just add -1, or subtract the bottom row from the top row, and you end up with 1, 0, 0, 1, -3, 0, which tells us that the coefficient on the first vector in C should be -3, and the coefficient on the second vector should be 0. Now that makes sense because notice this is just a multiple of that first vector, 1, 0. It's -3 times it. So that row reduction works, and it was a very easy row reduction. But anyway, our conclusion is that the coordinate vector of y with respect to C is -3, 0. If we had picked a different example, though, notice this vector y would have had something that's not just a multiple of one of them. We put it in the augmented position in this matrix, do some row operations, and the output will be a row reduced matrix on this side and some other vector on that side. That other vector will be the coordinate vector of y with respect to c. They just happen to be the same in this example. Don't be confused. Okay. However, we're going to do something else. We're going to do a second strategy, something that's going to generalize. So, because the problem is, this requires some row reduction. This requires a row reduction every time they hand us a vector y that where we know the coordinate vector of y with respect to b, but we don't know y itself. In other words, when we have the coordinate vector of y with respect to b, we're going to end up computing a linear combination in order to find y itself as a vector. And then we're going to put that vector in a matrix whose columns are the basis for C, the basis C, and then do a row reduction, and that will give us the coordinate vector. That's 3 steps that are tedious, okay? okay? So instead, we're going to use strategy 2, which is a little bit longer. We only have to do it once. In other words, we have strategy 1 is 3 tedious steps. Every time they hand you a coordinate vector with respect to b. But well, okay, let's actually see what strategy 2 actually looks like. So instead of computing directly the coordinate vector of y with respect to c, I'm going to let u1 be the first column of b, negative 1, 2, and u2 be the coordinate vector, the second coordinate vector, or the second basis vector. So 2, negative 1. Then instead, we're going to do something clever. We're going to compute the coordinate vector of u1 and u2 with respect to c. Interesting. So u1, c. And I guess for the sake of this problem, I'll just cheat and look at the book. It's negative 3, 2. We have to do the above problem in order to do that, right? We have to stick the vector 1, 2 right here and row reduce. Okay, we probably could just do that by inspection. Let's just do it real quick. 1, 0, 1, 1, negative 1, 2, augment, subtract row 2 from row 1. And this gives us 1, 0, 0, 1, augmented with negative 3, 2. Wow. So this equals negative 3, 2. Also, u2 with respect to c, for the same reason, just put a 2 and a negative 1 down here, and then subtract row 2 from row 1. And you'll end up with a positive 3, 2. Positive 3, negative 1. Okay? And now the question is, what is the coordinate vector of y with respect to c? Well, that is just the coordinate vector of y with respect to b times the matrix u1, u2. So negative 3, 2, 3, negative 1 times the coordinate vector of y with respect to b, which was given to us as negative 1, negative 2. Now, when we compute this, what do we get? We get negative 1 times negative 3 is 3. Negative 2 times 3 is negative 6. Add them together, you get negative 3 here. And then negative 2 plus 2 is 0. Okay. Now, before I tell you the next definition and theorem, which are really nice, let me just admire the beauty of what we just did. By doing this clever thing, what actually did we try to do? We tried to find a way to represent. So we have a way of representing y in terms of b, and we have a terms of representing b in terms of c. To get y in terms of c, we just have to do matrix multiplication. Now, the utility is, now suppose they gave us, if yb, this coordinate vector was, 12, 20. 12, 20. Okay, I'm going to have to put that thing in a matrix, row reduce, and end up with, first thing I have to do is, I can't put just 12, 20 into the matrix. I have to figure out as a linear combination, I need 12 times the first basis vector in B and 20 times the second basis vector in B. Add them together, that will give me the vector y itself with respect to the standard basis. Then I have to plug that thing, plug that thing into a matrix and then row reduce that matrix. Now granted, in this toy example, that row reduction is just one operation, so it's not so bad. It amounts to a matrix multiplication followed by a little bit of arithmetic on the coordinates of the output of that product. But instead, I can literally jump to the conclusion by just swapping out this vector with 12, 20. I'm not even going to write that down. I'll just tell you what the output is. It tells us that the coordinate vector of y with respect to c is 12 times negative 3 plus 20 times 3 is 24. And 12 times 2 minus 20 is negative 4. Sorry, positive 4. And we're done. I just pretended that I had a 12, 20 here and did matrix multiplication. Now, the good news is I have to do a bit of extra row reduction, one for each basis vector. And then I just assemble a matrix. And then after that, every time I want to convert one coordinate vector into another coordinate vector, it's just a matrix product rather than a row reduction. And the trade-off is that there are significantly fewer basis vectors than there are vectors I might want to transform, especially if I'm working in a complicated problem. So for that reason, we're going to define the change of basis matrix, which is this magic object that we were using. Okay, so let B and C be bases for a vector space V. Then the change of basis matrix, which it's like P with a subscript of a C and then a backwards arrow and then a B. That's the change of basis matrix from B to C. That is the n by n matrix whose columns are the coordinate vectors of uj, the basis elements of B, or the basis vectors inside of B, with respect to the basis C. Okay, I will be writing that as PCB because I'm not going to draw the arrow down there every time, and I'm not even going to use like fancy script letters. Nobody has time for that. Okay, so now we do have to be a little bit careful. What is up with this notation? So what's going to happen is we're going to be doing a lot of computing. You can see it right here in this theorem, but I'll explain that in a moment. We're going to be doing a lot of computing of like a matrix P. You'll see this notation actually. This is the notation that I learned. C P B like this. And then V with the coordinate vector, with the basis that your vector is written with respect to on the one side. Okay. And then the output of this thing would be CV, like this. Now, the idea is that this matrix is going to act as a machine that multiplies coordinate vectors. This actually, a better word is Rosetta Stone or translation software or something like that. It takes in vectors, which are coordinate vectors of your vector space V, which are written with respect to the basis B. So they're just vectors in Rn, where n is the dimension of your vector space. That's what a coordinate vector with respect to B is, right? We're going to take that coordinate vector, multiply by an n by n real number matrix, and the output will be another coordinate vector of length n. That will be the coordinate vector of your vector V written with respect to the basis C. In other words, if B was one language and C was another language, this matrix is the software that translates from one language to another. Okay, so And the translation process is just matrix multiplication. Yeah. Okay, so let's look at what this theorem is. By the way, that's why this weird notation you might see sometimes. They'll put the basis on like the one side, whatever. You multiply the vector on the right of your matrix, and the output is the same vector, but the basis that you're using to write this coordinate vector has changed. It's been translated from B to C. That's also why in this weird notation, the C comes before the B. It's because you have to multiply a B vector on the right, and the output will be a C vector. So that's why the order is there. It seems kind of counterintuitive because what did we do? We called it the change of basis matrix from B to C, and we like want to read right to left, like or left to right, but no. When we do matrix multiplication, it goes like from right to left in this case, right? So, okay, theorem 612. Let's formalize everything that we just said. First of all, for every x in your vector space of V, PCB times the coordinate vector of x with respect to B is the coordinate vector of x with respect to C. Okay? Property 2 is that, by the way, PCB is the only matrix that has this property. It is the unique matrix that sends every vector in V, sends the coordinate vector of every vector in V to the corresponding coordinate vector in C. Okay? And another amazing fact is that not only is PCB an invertible matrix, but the inverse of PCB is PBC. It's the change of basis matrix from C to B. So if you wanted to send your vector from B to C and back, that's like doing nothing to your coordinate vector. And sure enough, multiplying these two things by one another will give you the identity. And then multiplying a coordinate vector by the identity matrix is not going to change that vector at all, right? So, okay. So, this is most of what we're going to do from now on is examples. So this one says find PCB and PBC for the bases B, which is just standard basis for P2, the vector space of polynomials of degree less than or equal to 2. If you didn't see the last video, you should watch it. And then C is going to be, we did an example in that last video where we used the basis 1 plus x, x plus x squared, and 1 plus x squared. We're now going to figure out a dictionary to go between these two bases. And then we want to find the coordinate vector of 1 plus 2x minus x squared with respect to C. By the way, this vector, the coordinate vector of that thing, 1 plus 2x minus x squared, with respect to B, is 1 to negative 1. Because standard basis. How many times do I have to multiply by this guy, and this guy, and this guy? Well, 1, 2, and negative 1, right? Okay, so that's just an FYI. The real problem here is let's go and find the change of basis matrices. So to do that, we have to go and compute 1 plus x, the coordinate vector of 1 plus x with respect to, the coordinate vector of 1 with respect to C. Try to draw my script C's. Okay. Well, the coordinate vector of 1 with respect to C, well, we can do an easier way. This is what I was going to do. Okay. We're going to use a hack. We're going to use property 3 of this theorem. Okay. So first, what we want to do is compute the coordinate vector of 1 plus x with respect to b. It's going to be great. This is very easy. You can do this by inspection. How many, what linear combinations of basis vectors in B do you need in order to create this particular basis vector? Well, it better be 1, 1, 0. Remember, coordinate vectors are just vectors in Rn, and that's what makes them super nice, where n is the dimension of the vector space we're working in this case, P2, the set of polynomials of degree less than or equal to 2, has dimension 3. And so, yeah, so we're going to be working in R3 for most of this. Let's do the other two real quick. X plus x squared, written with respect to b, is 0, 1, 1. And 1 plus x squared, written with respect to b, that's a beta, b, is 1, 0, 1. Okay, now these are the coordinate vectors of elements of C, basis elements of C, written with respect to B. So by the definition, unfortunately, look at this C down here. We've switched the roles of B and C. That's okay, of like the bases B and C. So what we are able to compute is PCB. The change of basis, PBC. I got this backwards. The change of basis matrix from C to B is what we just computed. And its columns are 1, 1, 0, 0, 1, 1, 1, 0, 1. Now by property 3, was that 612? By 612, like property C or whatever, I don't know. We can just write down PCB as well. It's the inverse of PBC. And since I'm not going to just compute that matrix inverse live, I'll just tell you what it is. It's 1/2, 1/2, negative 1/2, negative 1/2, 1/2, 1/2, 1/2, negative 1/2, 1/2. You do like PBC, take the inverse, turn all the zeros into negative ones, and then divide everything by 2. That's not the general process, that's just what the shape of this matrix is as compared to the other one, if you like patterns. Okay, so this is the coordinate, this is the change of basis matrix now from B to C. We have a coordinate vector with respect to B, and we are asked to find the coordinate vector of that vector with respect to C. The good news is that's just a matrix product. So thus, the coordinate vector of 1 plus 2x minus x squared with respect to C is, take this matrix, multiply by this vector. And the output is, 2, 0, negative 1. You just do one vector times a matrix. There's a bunch of halves there, though, so I'm too nervous to try it live. Okay, and that's it. Notice how much easier that would have been, than what we could have done, which is like go and set up a system of equations and then row reduce. Yes, we did have to find a matrix inverse, but notice that's a row reduction that we would have had to do anyway. It's just that we augment with the identity and then do the row reduction. And as it turns out, the process for computing, I can't say that yet as a spoiler. Okay, I won't say it yet. Keep in mind that to compute this inverse, we had to do PBC augmented with I, 3, and then row reduce. Remember that. We're going to come back to it. So, I mean, it's not fun to have to row reduce, compute a matrix inverse. But what we're doing is challenging, no matter what we look at it. So, okay. So now we're going to do the same problem, but in a different vector space. So the basis B is going to be the standard basis for M22, which is like 1, 0, 0, 0, 0, 1, 0, 0, 0, 0, 1, 0, 0, 0, 0, 0, 0, 0, 1. The subscripts of the locations of the 1 are these. So E22 is the 0 matrix with a 1 in the 2, entry. Okay. And then C is this random basis, and we want to do an analysis on X, which is 1, 2, 3, 4. That is its coordinate vector with respect to, I guess, XB is 1, 2, 3, 4, like this. Wow. You can just shrink it down and put it in parentheses. Just remember. Yeah. Okay, great. So let's do it. Once again, what we have to do, so by the same strategy, right, we can find, and not the same strategy. This time, let's try to just go straight to PBC. That's the matrix whose columns are E11 written with respect to C, E12 written with respect to C, E21 with respect to C, and E22 with respect to C. Let's do it. Okay, so this is not so bad, right? First of all, actually, I'm just going to put an equals. This is not so bad. E11 written with respect to C. Well, fortunately, E11 is literally 1 times this basis vector. So 1, 0, 0, 0. That was not so bad. The next one. So how do you make that second one out of, how do you make the second standard basis vector? So how do you make 0, 1, 0, 0 out of the other ones? Notice the other ones have non-zeros in the bottom. The last 2 basis vectors have non-zeros in the bottom entry. So we won't be able to use those. Instead, we just need to use the first 2. And notice, if you want to get a 1 in this position, you can do 1, 1, 0, 0, and then get rid of the first entry. So this is 1 times the second one and -1 times the first one. So 1 times the second one and -1 times the first one. And 0 times the other ones, of course. Great. How do you do 0, 0, 1, 0? Well, that you can just do, we can follow the pattern. Do 1, 1, 1, 0, and then subtract the top 2 entries. So that'll be 0, -1, 1, 0. And the last one, how do you get a 1 in the bottom position? 0, 0, 0, 1. Start with 1s in all 4 positions and subtract the other 3. So 0, 0, -1, 1. That is PBC. Okay, we are asked to find the coordinate vector of x with respect to c. And that is just, it should be an equal sign. I don't know why my iPad is having issues with horizontal lines over there, but anyway, this is going to be PCB okay. I lied about this being PBC. This is PCB, of course. PCB, by the way, the amount of times that I've, even in this video, switched the order of B and C is about normal. It takes a little bit of working with these matrices to get the order right, because you have to reverse the order like what you think it's going to be, right? PBC is the matrix that takes in vectors in B and turns them into vectors in C, moving from right to left. And that's why it's important. I like putting it in brackets like this because actually we don't even need the brackets, but like, because you can do capital X now written with respect to B, and notice these B's match, right? And so it's a dictionary that goes from B to C, but you want, if you had the subscripts switched, then adjacent subscripts wouldn't match, and that means you're starting in the wrong language, right? But fortunately, PCB by definition, PCB, oops, too far, literally is the change of basis matrix from B to C. That's the important part. Okay, so right, and so the point is we have the right matrix. So the coordinate vector of x with respect to C is quite literally this matrix times this vector, the one that we computed before. 1, 2, 3, 4. And when you do that product, you get the vector 1 minus 2 is -1, 2 minus 3 is -1, 3 minus 4 is -1, and 4 times 1 is 4. -1, -1, -1, 4. You can verify that by doing -1 times this, plus -1 times this, plus -1 times this, plus 4 times that. You just ask, how many times are things being added and subtracted? The top left corner gets subtracted 3 times but added 4 times. The top right corner gets subtracted 2 times but added 4 times. The bottom left corner gets subtracted once and added once, or added 4 times. And then the bottom right corner doesn't get subtracted at all, but it does get added 4 times. That's how you build 1, 2, 3, 4. Okay. Still, that's kind of a lot of work. I'd like to show you a second strategy real quick. So strategy 2. By the way, this was strategy 2 for the other that we used in the other case, right? Compute a change of basis matrix and then do some computation. And notice we're already working in 4-dimensional space, or a 4-dimensional vector space. And so if we were to do strategy 1 from the previous problem, it would be way too much work already. This was definitely the way to go, because notice our last step was to just do a matrix product, right? And we could have done, they could have handed us any vector, it didn't matter. Sorry, any matrix 2 by 2. It's a vector inside the vector space we're working in. Okay, so here's something interesting. Suppose that E is the standard basis. Wow. This is not going to work. We can do it, but suppose E is the standard basis. In our case, that means E is equal to B. But there is a property that we will prove, we will show, that P C E times P E B. I have to write this, I'm writing the subscripts very carefully, is PCB. Why is that? Because what does C and what are B, C, and E? Each of them we're viewing, each is a basis, of course, for some vector space. But if you're viewing it as a language, and the change of basis matrices are translations from one language to the other one, from the language on the right subscript to the language on the left subscript, then what is this? So this matrix product that I've written on the left-hand side of the equal sign is, what does it mean to multiply that matrix by a vector? It means take your vector, translate a coordinate vector. The only input that makes sense is a coordinate vector with respect to B. Multiply that coordinate vector by PEB. You'll get a coordinate vector with respect to E. Multiply that coordinate vector by PCE, and you end up with the coordinate vector with respect to C. So in other words, you input a coordinate vector with respect to B, and you get out a coordinate vector with respect to C. But by the second property of theorem 612, there's only one matrix that has that property, and it's PCB. That has that property for every vector. But of course, this one does it for every vector, right? So PCB is exactly this thing, and it didn't matter what basis so we could really say, instead of E being any basis, or being the standard basis, we could have said E is any basis, and this will be true. But when E is the standard basis, in our example, this is the identity. In the book's example, it is something else. It's like the identity, but you switch row. It's like an elementary matrix in the book, where you switch rows 2 and 3. And then when you go and do it, you'll get like when you go and do it, if you want to go and see what the book is talking about, doing it their way, you don't get a nice off diagonal like this. You get some weird jagged matrix. But that jaggedness is accounted for by this elementary matrix. For us, it's the identity matrix because we cheated, I guess. I don't know. Great. Okay. Well, anyway, the whole point is, since we were able to notice how easily we were able to construct PCB in this example, that was because B was the standard basis. Like, how difficult is it to construct, the change of basis matrix that changes from the standard basis to something else? Not very difficult. And vice versa, to change from some random basis to the standard basis. Okay, that requires a matrix inverse, like we saw in the previous problem. Still not so bad, all things considered. But what about changing from one arbitrary basis to another one? Well, as it turns out, this little fact that we have about matrix multiplication is clutch. It is it will smooth it out. So here's the theorem. The theorem is a wonderful, wonderful theorem that basically says as long as you can row reduce, you can always change between bases. So let B and C be bases for V, arbitrary. And then let fancy B and fancy C, but we're going to let B and C be the matrices U1 up to UN, matrices of coordinate vectors of U1 up to UN, with respect to some basis E. And C do the same thing, V1 up to Vn with respect to E for any basis E. Then if you take the two matrices that you just wrote down, augment them, C augmented with B, like that, and then row reduce C to the identity. The matrix that shows up on the other side of the augment bar is exactly PCB. It's the change of basis matrix from B to C. We just put from and to help us remember this. So, and we'll do an example of that in just a second. But let's just do it real quick. We'll do, well, yeah, we'll do the proof real quick. Notice that columns of PCB are coordinate vectors uj written with respect to C, right? This is the definition of PCB, and the UJs are like basis vectors in B, and we're taking their coordinate vectors with respect to C and putting them in a matrix. That's what PCB is, right? And I'm just gonna write these as like, I don't know, little p 1j, p2j, dot dot dot, pnj, like this, right? Lowercase p's, like I'm just saying these are numbers that go inside of this column. Then, if you wanted to take, so like, what is this? What are we doing here? This is a recipe. Like, what do these coordinates measure? These coordinates measure exactly what numbers you have to multiply the columns or the basis vectors in C by in order to compute uj. Let me write that uj. So uj itself is quite literally p1j times v1 plus p2j times v2 all the way up to pnj times vn, right? Well, if we wanted to write this with respect to, okay, so what is uj written, but with respect to E then? Well, that's just literally, it's literally this with respect to E, right? But that just requires us to do a bunch of linear combinations of the VJs, each one written, sorry, the coordinate vectors of the VJs, each written with respect to E, whatever our basis E is. So P1J times the coordinate vector of V1 with respect to E. Plus, I'm just going to write dot, 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 all the way up to PNJ times the coordinate vector of Vn with respect to E. Okay. But that is just okay, I don't know if I can squeeze it here. Okay, I'll squeeze it and then I'll write it correctly. Actually, I don't. Yeah, I will. It's v1 written with respect to E, dot dot dot, vn written with respect to E. Notice this matrix is quite literally just P E C, PCE, PCE times, but also times this vector. It is PEC, geez. PEC times the vector uj written with respect to C. That's where the P's came from, right? Uj written with respect to C sent through the translation matrix, change of basis matrix, over to E. So we've written the coordinate vector of uj with respect to E as a linear combination of the columns of this change of basis matrix. Notice, oh my goodness. I said the whole thing. I said it backwards, all of it. This is a linear combination of coordinate vectors for the vectors in C written with respect to E. This is the translation matrix from, it doesn't matter. It doesn't actually matter what it is. But this is the translation matrix from, I think I'm just going to leave it. I'm going to leave it as is. Because notice, we just have to row reduce the following matrix with respect to row reduce the following matrix. Okay, it looks like this. I'll just write it. V1E, V1, Vn E, all the way up to Vn E. This thing augmented with, okay, I'll write what this is. This is, by the way, this is written correctly. Notice we did a matrix product. The thing that was tripping me up just now was normally I'm used to writing it with brackets. Notice if you do this actual matrix product, what is the thing that we've written down here? It's the coordinate vector of uj with respect to E. And that is exactly the thing that we're going to put in our augmented matrix. If you row reduce that, what we'll end up with is the coordinate. This is a recipe for the coordinate vectors of B with respect to C. So let me just write that. Row reduce that to obtain the identity augmented with uj with respect to B. Sorry, with respect to C. But notice this entire so in other words, we were able to obtain the first column of PCB. But we were able to do it by writing everything with respect to an arbitrary basis. Well, now so now we just construct the following matrix: C augmented with B. That's because there are n. We have to do this. Okay, we have to do this procedure n times. And what are we after? We're trying to compute the change of basis matrix from B to C. So that's PCB, right? And we're able to do one column by row reducing whatever this matrix is. But okay, go and do that for a different column. Notice our choice of J didn't matter. So do that. So now we have to row reduce again to find another column. And we do that one time for each of the uj column vectors that we're hunting for. Well, that is noted, but like when we do that, the matrix that we're row reducing is the same matrix every time. It's this matrix that has to get row reduced. That notice, at no point did we appeal to a different collection of VNs. Like the P's are the things that are changing. every time we pick a different a different column that we're going to go and try and solve for. So the matrix C augmented with B, notice C is quite literally this matrix. By definition, it's V1 all the way up to Vn, all written, coordinate vectors all written with respect to E. And what's happening on the right-hand side, each time that we're doing it, we're trying to compute a uj with respect to E. Well, each one of those is one of the columns inside of B, right? And that was what gave rise to the augmented matrix that we had to row reduce. Do that n times, one for each of the columns. That's the same as row reducing this augmented matrix, C augmented with B. But this is just an n by 2n row reduced matrix, or augmented matrix. And so when we row reduce it, the thing that we get out of it is the identity on one side and then the change of basis matrix, PCB, on the left-hand side. That's it. That was a sketchy proof, mostly because I got distracted by subscripts like 4 times. Okay, but this is correct. And the book does a good job of going through the same exact proof. They do it before the statement of the theorem, whereas we did it afterward. Now I just want to show you how to apply that theorem. The first thing that I want you to notice is that if one of your bases is the standard basis, then in one case, actually, let me just do it smaller. So, okay, suppose B is the standard basis. C, and then C will be some random one. Okay, when we do this process, notice we can pick any, I don't know why I put an arrow there. We can pick any basis E and do this process and it will work. Our choice of basis E didn't actually matter because it passed in the end as just every single time, as long as you have an n by 2n matrix augmented with all of the vectors inside of C and B written with respect to whatever this in-between basis is E. Always when you reduce to the identity on the left, the matrix that pops out on the right will not be referencing that in-between basis E at all. And by the way, if you row reduce the other way, I'll just draw an arrow here. By just either switching the augment or computing the inverse of PCB on the right, you can also row reduce this to PBC augmented with the identity, right? This is just something to keep track of. Now, so choose E to also be the standard basis. When you do, okay, you have the standard basis for B and E. What are the coordinates of B written with respect to E? They're just the n by n identity. And the coordinate vectors of C written with respect to E are just whatever you have to do. You can read them out of the basis C. So it's going to be, actually, let me just write this. It's going to be C augmented with I. And if you want to, do, so PCB, this C is like the coordinate vectors of your basis C written with respect to the standard basis, which is, we've already done that a couple times in this video. It's pretty straightforward. But that tells us that PCB, the change of basis matrix from B to C, is nothing other than C inverse. And it's even better than that. Apparently, C itself literally is BC. In other words, we can just go and either read off PBC or just compute a matrix inverse to find PCB. That is exactly what we did in those first two examples. Notice we had one case was one way and the other case was the other way. Very straightforward. But then also we can verify. We can verify this last example by noticing that this matrix is PCB, which is, how did we obtain this matrix? We obtained it by writing each of the basis vectors of the identity, the standard basis, with respect to the basis C, right? That was this matrix exactly, and it was a translation from B to C. And we started with basis vectors in B, and we obtained basis vectors in C. And sure enough, this is the change of basis matrix. Its inverse would have been PBC, the change of basis matrix from C back to B. And by the way, all we have to do is take its inverse if we want to go backwards. If you had an arbitrary, two arbitrary bases, you can write each of them with respect to the standard basis, and then just row reduce to get the change of basis matrix between them. Row reduce the augmented matrix. Okay, so that was a lot. The homework is very forgiving on these topics. And I guess this is our last video for the summer semester, so I will not see you in the next video.